Hi everyone, this video is going to be looking at heating and consequently cooling curves by taking a look at these graphs that we can generate that compare temperature to either time or more commonly heat added to a particular substance. So the very first thing I want to reiterate before getting into this idea of heating curves is the link between temperature and kinetic energy. Remember from our very first video of this unit that temperature is just a measurement of average kinetic energy. So I'm going to write it right in here on our y-axis to remind you that as we change temperature, what we're really changing is average kinetic energy. So these types of graphs are going to plot over time or as heat is gradually added to a substance, what types of changes are taking place. So in your head, you can imagine either some form of metal, you can imagine a block of ice, some kind of solid substance. If it's really, really, really cold, or even if it's just below that substance's freezing point, we can take that solid and we can gradually heat it up. That purple line is going to represent our substance in the solid phase as it gradually goes from being a cooler solid to a slightly warmer solid. Now, at some point, that solid is no longer going to be completely solid. It's going to want to start changing. It's going to want to start melting. So when that process starts to happen, what we see on our graph is that we get a flat line. You guys know that water melts and freezes at 0 degrees Celsius. It just depends on whether you're adding heat in or taking heat out. That melting or freezing process does not happen instantaneously. If you want to get an ice cube to fully melt, you have to keep adding heat, whether it's from just the outside environment or from your hand. That's what this flat line is representing, that we're changing from solid into a new state of matter, let's say liquid. And once we have that liquid, we can continue to add heat and that liquid is going to get warmer and warmer. Still a liquid, you know from thinking about vapor pressure before, that as we make this change, the vapor pressure of the liquid is likely to be increasing, but that's not changing its state entirely. That only happens once we hit a substance's boiling point. So we'll draw in a line to represent that at a particular temperature, a substance is going to want to make the change from liquid into our final state of matter, gas. So that red line again is flat because boiling happens at a particular temperature, but it takes some time or it takes some energy to be put in order to get that change completely finished. So if we look at all parts on this curve, we can start making some conclusions about what's changing and what's not. As I move from the very bottom point of my curve right to where it starts to get flat, that time when our substance is a pure solid, what's changed from this point to this point is the temperature of the substance. So what that tells me, if temperature changes, that must mean average kinetic energy has changed. And in this case, because we're adding heat's a form of energy. In this case, the form that we're adding is average kinetic energy. Average kinetic energy will go up because temperature went up. Temperature is our measurement of how fast our molecules are moving. But what about the green line? And notice here that what's happening is that the phase of matter is changing, not the temperature. That flat line indicates to me that average kinetic energy is just doing nothing. It's sitting there, not declining, not increasing. It's staying completely constant. But you can tell from our axis that heat is still being added. We have to warm up that solid substance in order to get it to melt. We've got to heat it up. But the heat that we're adding is no longer associated with kinetic energy. Instead, it's associated with pulling those solid particles apart so that they can become more like a liquid. So that type of change is associated with potential energy. So here it's potential energy instead of kinetic energy that's changing. So notice that only one type of energy is going to change at a time. When average kinetic energy increases, potential energy stays the same. When you're in the middle of a phase change, it's your potential energy that's increasing, and your average kinetic energy will be what stays the same. Similar things can be said for the remainder of the curve. Along this slanted line, we see an increase in average kinetic energy because there's an increase in temperature, whereas potential energy stays the same. We hit a flat line. Temperature is not changing, so that must mean average kinetic energy stays the same. But because heat is still being added constantly, a type of energy has to change. It must be potential energy that's increasing here. And last but not least, just like every other slanted line, when this substance is a pure gas, its temperature is increasing, so average kinetic energy must increase. And if it's the kinetic energy that's increasing, our potential energy must stay the same. All of these changes are going to be true whether we're looking at a heating curve where heat is being added over time, or if we flip things around on you. Let's say instead of adding heat, we're releasing it. Maybe I've got a gas, a sample of maybe oxygen or something. I start in the gas phase and I take heat out. We're doing exothermic changes instead of endothermic ones. I can cool that gas down until it begins to condense. I can then take that pure liquid and cool it down until it begins to freeze or solidify. And I'm going to be left with a pure solid whose temperature I can decrease. The same situation applies on this now cooling curve where heat is being released. Along my flat lines, we see average kinetic energy staying the same because temperature is not changing, stays the same. However, we know one form of energy has to be changing because heat's being released during this process. That form of energy must be the potential energy. We're losing heat to the environment, so that means the potential energy of our substance must, in this case, be decreasing. So as we cool our pure substance, while the phase changes occur, potential energy is decreasing. That means along our slanted lines, potential energy stays the same at all 3 points, but it's our average kinetic energy that is decreasing because we can just replace that average kinetic energy with temperature. So know these relationships, know the shapes of the graphs, know the phase changes and the links between what's going on a molecular scale and what's happening with kinetic energy and potential energy.